So, today I will take the evening also, right, because yesterday I have some work, that is why I did not take the class. Today I will take the evening class also. First we are teaching about the thermodynamics. Under the thermodynamics we taught about the Maxwell's laws of the thermodynamical equations and their consequences I told to you. The subsequent topic is thermodynamic potentials. Those 4 potentials I informed you. The subsequent topic of the 4 potentials also I am giving to you. So, grand potential and Gibbs-Deham relation, those things I gave to you. Availability, those things I gave to you, right. So, those things enough for you according to your CSR standard I taught. So, the subsequent topic of a thermodynamic potential, the Maxwell equations are very important. Maybe these Maxwell equations 2-3 classes I have to take. The Maxwell equations part 1, this one I am teaching now. So, maybe evening also have to take the Maxwell equations applications, and tomorrow also I will take the Maxwell equations applications. Maybe at 3 classes I have to take and I will wind up. After wind up these Maxwell equations, we are going to teach about the which one it is, that is the chemical potential. Already we defined the chemical potential while I am teaching the thermodynamical potentials. We are defining the chemical potential, but even though we have to taught again the chemical potential is quoted according to your syllabus, that is why I will teach to you. First we have to take so Maxwell relations. How many Maxwell relations are there to explain the thermal body or thermal potentials, the interrelation between the thermal body and thermal potentials? So, we have how many? So, we have total 4 Maxwell equations are there. How we have Maxwell equations in electromagnetic theory, the similar way in thermal physics there is a 4 Maxwell equations are there. So, those 4 Maxwell equations we have to teach in this class, clear. So, that is very important. Once again you have to concentrate on that. So, not only that, so you are going to take so what you are going to take, once you have to see the first thermodynamic relation. What is the first thermodynamic relation? You know that the internal energy, the change in internal energy du is equal to according to the first thermodynamic relation, potential relation, TdS minus PdV. Yesterday we discussed this one, TdS minus PdV, correct. So, this is the first thermodynamic relation. What is the function of this internal energy? Is the function of thermodynamical variable S and V. Internal energy is the function of S and V you have to take. First you able to take this expression and you have to define the partial derivative dou u by dou s at a constant volume you have to take. So, dou u by dou s at constant volume is equal to what we have to write it is, that is the temperature. Similarly, you have to take dou u by dou v at a constant entropy is equal to what you able to get it, you are going to get minus pressure you are going to get. Suppose du is a perfect integral or perfect differential you have to take. Suppose you are going to take it as a du is a perfect differential. Which differential it is? Perfect differential. Du is a perfect differential, then we are going to take it as a du is a perfect differential, then you have to take, you have to apply. So, what you have to apply? Dou u by dou s at a constant volume, you able to take it as a dou by dou v of dou u by dou s at a constant volume. Dou u by dou s at a constant volume is equal to dou by dou s of which one we have to write it is dou u by dou v at a constant dou u by dou v at a constant entropy you are going to write. At constant entropy you able to take. So, therefore, what is going to happen? So, this entire term we are defining dou u by dou s at constant volume is equal to dou u by dou s at constant volume is equal to dou t by dou v, dou t by dou v. Inside one you have to take it as a constant one you have to take, which is equal to dou t by dou v at a constant entropy is equal to dou u by dou v at a constant entropy is equal to minus dou p by dou s. Which one you have to write? This inside one you able to take it as a constant one. This relation we are going to call it as a thermodynamic first relation. What relation it is? This is the thermodynamic first law. This is the first thermodynamic. Which one you have to write? It is thermodynamic Maxwell relation. This is the first thermodynamic Maxwell relation. First thermodynamic Maxwell relation is what is the first thermodynamic Maxwell relation? That Maxwell relation is dou t by dou v at constant s is equal to minus dou p by dou s at a constant v. This is the first thermodynamic relation. How we have to write? Once again you able to take it as the first thermodynamical Maxwell equation is equal to what we have to write it is dou t by dou v at a constant dou t by dou v at a constant s is equal to minus of dou p by dou s at a constant volume, which is equal to what we have to write it is dou square u is divided by dou s into dou v. This relation we call it as a thermodynamic first relation of the Maxwell. This is the first thermodynamic relation of Maxwell. What is this? This one is Maxwell's. Maxwell is a great scientist. Maxwell's first thermodynamic relation. Maxwell's first thermodynamic relation. What is that relation? That relation is going to take it as a, so dou t by dou v at a constant entropy is equal to minus dou p by dou s at a constant volume, which is equal to minus dou square u by dou s into dou v. This is the first thermodynamic relation by using the internal energy we are defining. Not only that, so we able to take the second thermodynamical relation. What is the second thermodynamical relation? You know that enthalpy, the change in enthalpy, Helmholtz free energy, the change in Helmholtz free energy is equal to minus s dt minus p dv, minus s dt minus p dv. So therefore our Helmholtz free energy is the function of whom? Is function of temperature and volume. So is the function of temperature and volume. So therefore what we have to write it is dou f by dou t at a constant volume is equal to minus s. Similarly you have to write it as dou f by dou v at a constant temperature is equal to minus p you are going to take. At constant temperature is equal to minus p. So therefore what we have to write? The change in Helmholtz free energy is a perfect differential. Which one you have to write it is? df is a perfect differential. What we have to write it is? If df is a perfect differential, we are going to write it is, if df is a perfect differential, we are going to take so dou by dou v at constant term I am writing. Dou by dou v, we have to take it as a dou by dou v at a constant. Which one we have to write it is? Dou f by dou t at a constant volume, which is equal to dou by dou t into what we have to write it is dou f by dou v at a constant temperature we have to take. So what we have to write it is dou F by dou T at constant volume is equal to minus S. So therefore minus dou S by dou V at a constant temperature, inside one you have to take at a constant temperature, which is equal to minus, what is this? So this one you have to take it as a minus dou P by dou T, dou P by dou T, inside one you have to write it is that constant volume, minus minus get cancelled. So therefore dou S by dou V, dou S by dou V, dou S by dou V at constant temperature is equal to dou P by dou T at a constant volume. This relation we call it as a second Maxwell's thermodynamic relation. This is the second thermodynamical Maxwell, second Maxwell's thermodynamic relation, second Maxwell's thermodynamic relation, the second Maxwell's thermodynamic relation is equal to dou P by dou T at constant volume is equal to dou S by dou V at a constant temperature. How we have to write this one also I am going to take it as a in terms of the second Maxwell equation, while you have to take it as a Helmholtz free energy. How we have to write? So dou P by dou T, dou P by dou T at a constant volume is equal to dou P by dou T at a constant volume is equal to dou S by dou V at a constant pressure, dou S by dou V at a constant temperature, dou S by dou V, what we have to write it is at a constant temperature you able to take, which is equal to what we have to write it is. So we are going to take dou square F is divided by dou square F is divided by dou T into dou V we have to write here. Dou square F is divided by dou V into dou T we have to take. Here also dou square U by dou S into dou V. How I am writing? Here also you able to take it as a, this is the second Maxwell's thermodynamical relation. This relation is very very important. So what is this relation? This relation we are going to take it as a second Maxwell's thermodynamic relations, second Maxwell's thermodynamic relation. Second Maxwell's thermodynamic relation is this one, dou P by dou T at constant volume is equal to dou S by dou T at a constant temperature, which is equal to dou square F is divided by dou T into dou V you have to write it is. So therefore one more thing you have to take, that is the third thermodynamic relation. How we able to take the change in heat function, that is enthalpy, dH is equal to TdS plus VdP, TdS plus VdP, you know that TdS plus VdP. So therefore our enthalpy is a function of whom? Our enthalpy is the function of entropy and pressure. So therefore what we have to write it is dou H by dou S at a constant pressure is equal to temperature. Similarly you have to write it is dou H by dou P at a constant entropy is equal to what we are able to take it as, that is the volume you are going to take at a constant temperature is equal to volume. Similarly dH is the change in enthalpy is a perfect differential. If you have to take a perfect differential, the change in enthalpy is a perfect differential. So therefore what we have to write it is you able to take so dou by dou P of dou H by dou S at a constant pressure is equal to dou by dou S of dou H by dou P at a constant, which one we have to write it is entropy. But you know that dou H by dou S at constant pressure is equal to dou T by dou P, dou T by dou P. Inside you have to take it as a constant at S. So dou H by dou P at constant entropy is equal to what we have to write it is dou V by dou S. Inside one you have to take it as a, that is the, which one it is, that is pressure is constant you have to take. So therefore what we have to write it is, this is the third Maxwell thermodynamic relation, third Maxwell's thermodynamic relation, third Maxwell thermodynamic relation. What is that third Maxwell thermodynamic relation? Dou T by dou P at a constant S is equal to dou V by dou S at a constant pressure. This one also we have to represent the third Maxwell relation, while you have to take it as a enthalpy you have to write. So dou T by dou P at a constant entropy is equal to, at a constant entropy is equal to dou V by dou S at a constant pressure, which is equal to dou square H is divided by dou P into dou S. This is the third, which one you have to write it is third Maxwell's thermodynamic relation, third Maxwell's thermodynamic relation. What is the third Maxwell's thermodynamic relation? The third Maxwell's thermodynamic relation is going to take it as a dou T by dou P at a constant entropy is equal to dou V by dou S at a constant pressure is equal to dou square H is divided by dou P by dou S. Clear? So dou square H is divided by dou P into dou S. Now I am going to take the fourth Maxwell relation. What is the fourth Maxwell relation? Once you have to see, according to the Gibbs free energy, this Gibbs free energy we also call it as a thermodynamical potential. So this dG is equal to, what we have to write it is VdP minus SdT. dG is equal to VdP minus SdT. Therefore G as a function of whom? G as a function of pressure and temperature. So therefore what we have to write it is dou G by dou P at a constant temperature is equal to volume. So from this expression I have to write. Similarly you are able to take dou G by dou T at a constant pressure is equal to minus entropy you are going to take. Same procedure I am following if dG is a perfect differential. dG is a perfect differential. You have to take it as a dG is a perfect differential. Then what we have to write it is dou by dou T of, we are going to write it is dou by dou T of dou G by dou P at a constant temperature is equal to dou by dou P of dou G by dou T at a constant pressure you have to write. So this term, entire this term, which is equal to what V, you are going to take it as a dou V by dou T at a constant pressure is equal to dou G by dou T at constant pressure is equal to minus S dou S by dou P at a constant temperature you have to write it is dou S by dou T, dou S by dou P at a constant temperature. This expression we are going to take it as a fourth Maxwell's thermodynamic, what is it is fourth Maxwell's thermodynamic relation. Fourth Maxwell's thermodynamic dynamic relation. What relation it is? This relation we call it as a fourth Maxwell thermodynamic relation. Therefore, we have to write the fourth Maxwell thermodynamic relation is how we able to write here. Once you have to see dou v by dou t at a constant pressure is equal to minus dou s by dou p at a constant temperature minus dou s by dou p at a constant temperature, which is equal to dou square g is divided by dou t into dou p. This is the fourth Maxwell. Which one you have to write it is? This one we have to take it as a fourth Maxwell's thermodynamic relation. Fourth Maxwell's thermodynamic relation. What is the fourth Maxwell's thermodynamic relation? That fourth Maxwell's thermodynamic relation is equal to dou v by dou t at constant pressure is equal to minus dou s by dou p at a constant temperature, which is equal to dou square g by dou t into dou p. These are the four Maxwell equations we derived, right? So these are very important. You have to remember in your competitive examination. Now we are going to take it as a applications of the Maxwell equations. So what are the applications of the Maxwell equation? The first application is Clausius-Clapeyron's latent heat equation. Which equation is? The first one is Clausius-Clapeyron latent heat equation. We call it as a first Maxwell's application. The Clausius-Clapeyron's latent heat equation relates the change in melting point or boiling point, changing melting point or boiling point with change in pressure. So that is the relation of Maxwell's Clausius-Clapeyron relation. How we have to derive this one? From the Maxwell's second law of thermodynamic relation. What is the second law of thermodynamic relation? Dou p by dou t at a constant volume is equal to dou p by dou t at a constant volume is equal to dou s by dou v at a constant temperature. Dou s by dou v at a constant temperature. This is the thermodynamic second law of thermodynamics. Now you have to multiply above expression on both sides. Multiply. Which one you have to write it is? Multiply with the temperature on both sides. You have to multiply on both sides. You able to take it as a, you are going to write it is multiply. What will happen? You have to say t into dou p by dou t at a constant volume is equal to t into dou s by dou v at a constant temperature. We are going to write it is clear. Now you able to take so t into dou p by dou t at a constant volume, t into dou p by dou v, dou p by dou t at a constant volume, dou p by dou t at a constant volume is equal to, you are going to take it as a TdS. TdS is equal to dou q is divided by dou v at a constant temperature. We have to take at the constant temperature. So dq will give, so what we have to write it is this dq will used as a latent heat. So that latent heat I am using. So because we call it as a latent heat equation, we are going to call it as. So that's why we are going to take dq is equal to latent heat. You have to take the temperature into dou p by dou t at a constant volume is equal to. So we have to take it as a dq is equal to L. So dv is equal to, we are going to write it as a V2 minus V1, that changing the volume V1 to V2. At a constant temperature you have to use. So whatever it may be, you able to take it as a constant temperature you have to take. So this temperature you have to bring into this side. So what will happen, you have to see dou P by dou T is equal to the rate of change of pressure. Dou P by dou T is equal to what we have to write, 1 by temperature into L is divided by V2 minus V1. This expression we call it as a, which expression it is? Clausius-Clapeyron equation. Clausius-Clapeyron latent heat equation. So therefore, what is your Clausius-Clapeyron latent heat equation? Dou P by dou T is equal to L by T into 1 by V2 minus V1. L by T into 1 by V2 minus V1. This equation we call it as a latent heat equation. So which equation it is? This is the Clausius-Clapeyron latent heat equation. This is also known as a Clapeyron's equation. Which equation it is? Clapeyron's equation. It gives the rate at which the vapor pressure must changes with temperature for the two phases to coexist in equilibrium. So must changes with temperature, the vapor pressure must changes with temperature. dP by dt, the rate of vapor pressure is inversely proportional to temperature, and for two phases to coexist in equilibrium, that time this one is existing. This is very important equation. This equation we call it as a Clausius-Clapeyron equation. Which equation it is? This is the Clausius-Clapeyron equation. What is the significance of the Clausius-Clapeyron equation? When a liquid boils, suppose you have to take a liquid boils, so what will happen? Obviously your V2 is greater than V1, hence V2 minus V1 is the positive. If it is a positive, so that the rate of change of pressure also positive. This means that the boiling point of the liquid rises with the increase in pressure, and vice versa. The boiling point of liquid rises with increasing in pressure. The boiling point of liquid, what will happen? If you have to increasing in pressure, the boiling point of liquid also rises. Clear? So not only that, for substances like wax, sulfur, metals you have to take which expand on melting. So V2 minus V1 is positive. So therefore here also the melting point rises with increasing in pressure. The melting point rises in increasing in pressure. So not only that, for substances like cast iron, ice, gallium, bismuth you have to take etc., which contract on melting point. Contract on melting point means V2 minus V1 is going to become as a negative. Therefore, and hence dou P by dou T are negative. This indicates that the melting point decreases. The melting point decreases with increasing in pressure while you have to take the substances. Clear? So based on the substances, our melting point will be increased and decreasing takes place. The equation also known as also explains the regulation of ice. What is the regulation of ice? When two pieces of ices are pressed together, they form a single piece. This phenomena we call it as a regulation. So what is the regulation? When two pieces of ices are pressed together to form a single piece, such type of phenomena we call it as a regulation phenomena. Clear? So this equation also explains the regulation of ice. When the two pieces of ice are pressed together, they form a single piece. This phenomena is known as a regulation phenomena. Clear? So this is very important. Like this you have to remember. This is the physical significance of the Clausius-Clapeyron equation. Now you know that Stephen-Boltzmann law using the Maxwell equation. Stephen's-Boltzmann law. Stephen's-Boltzmann law we are going to be derive by using a Maxwell equations. How we are going to derive the Stephen's-Boltzmann law by using the Maxwell equations? You have to see here. So according to the Stephen's law, total radiant energy E emitted per second from unit surface area of a block body is proportional to the fourth power of its absolute temperature. What we have to write it is, the energy is proportional to the fourth power of absolute temperature we have to take. So therefore the energy is equal to, you have to take it as a sigma here Stephen's constant into T to the power of 4. So what is the sigma, where sigma is equal to, so what is your sigma? Sigma is the Stephen's constant. Which constant it is? It is a Stephen's constant. This Stephen's constant is universal constant, means wherever you go, the Stephen's constant won't be changed. That is 5.672. 5.672 into 10 to the power of minus 8. 10 to the power of minus 8 joule second inverse. Joule second inverse meter inverse Kelvin to the power of minus 4 you have to write, or this unit you able to take it as a watt for meter square into Kelvin to the power of 4 also we are going to take. Clear? So this is very very important. This is the Stephen's constant. So many times your competitive people are asking the values also. So that's why all the constants you have to keep at one place and daily you have to muck up, then only you able to remember these formulas. Now we need to calculate derivation from a Maxwell's thermodynamic relation. How we have to write it is, by the thermodynamic second law of thermodynamics, you know that by second law of second Maxwell's thermodynamics law, second Maxwell's, which law you are going to take it as? Thermodynamic law. Second Maxwell's thermodynamic law you have to take. What is the second thermodynamic law or relation? So this relation you have to going to take it as a not law. This is the relation you are going to take. What is that relation? Dou S by dou V at a constant temperature. Dou S by dou V at a constant temperature is equal to dou P by dou T. Dou P by dou T at a constant volume. This is the second thermodynamic Maxwell relation. This equation you have to take it as a equation number 1 you have to take. Based on this equation number 1, what we have to write it is, you are going to take according to the thermodynamic first law, dq is equal to du plus pdv. dq is equal to du plus pdv. But your dq is equal to TdS. This is the thermodynamic second law. So therefore, so this TdS is equal to, we are going to write it as TdS is equal to du plus pdv. TdS is equal to, what we have to write it is du plus pdv. So therefore ds is equal to, we are going to write it as 1 by t into, ds is equal to 1 by t into du plus pdv. We are going to take 1 by t into du plus pdv. This is the equation number 2 you have to take. So now equation number 2 you have to substitute in equation number 1. So what is your equation number 1? Equation number 1 is a thermodynamic second law of the Maxwell equation. So therefore instead of ds you have to write it as 1 by t into, you are going to get it 1 by t into dou u by dou t. Dou u by dou t at a constant temperature pressure. So what we have to write it is dou v by dou v get cancel. You are going to get it as a pressure is equal to, you able to get dou P by dou T, dou P by dou T at a constant volume you are going to get. This is the equation number 3 you have to write. It is clear. So, based on the thermodynamic equation, I am going to define. So, I am going to get it that one. So, from this equation what we have to write? So, what we able to take from this equation? We have to rearrange. So, dou U by what we have to take? Dou U by dou V at a constant temperature plus pressure is equal to dou U by dou V at a constant temperature pressure is equal to T into what we have to write it is dou P by dou T, dou P by dou T at a constant volume. This is the expression you have to take. This expression you are going to take it as a equation number 4 you have to take. Here the following 2 points should be remembered. The first one is, according to the electromagnetic theory, the block body of radiation in an enclosure exert a pressure P on the walls which is equal to 1/3 of the energy density. Thus, what we have to write it is our pressure is equal to 1/3 of the energy density. This one you know that our pressure is equal. The second one is, if V be the volume of the enclosure and U is the energy density of the radiation, then the total internal energy can be defined as U into V. You able to take. How you have to write it is U into V you able to take. Based on these expressions you have to substitute in equation number 4. So, therefore, what will happen? You have to see from equation number 4 our expressions will become, from equation number 4 our expression will become. So, what will happen? You have to see dou by dou V. Instead of this you have to write it as a U into V, energy density into volume at a constant temperature, plus U by 3, P is equal to U by 3, which is equal to, so T by 3 into, we are going to write it as a dou U by dou T. You are going to take dou U by dou T at a constant volume you are going to write it. So, now you know that, so you have to differentiate and you able to take that value. You are going to get it as a U plus U by 3, which is equal to what you are going to get it. So, T by 3 into, that is the temperature, into dou U by dou T, you are going to get it, dou U by dou T at a constant value. So, U plus U by 3 is equal to, you are going to take it as a 4U by 3 you are going to get. How much you are going to get it? So, 4U by 3, which is equal to T by 3 into dou U by dou T, 3 get cancel. Now, you have to rearrange the expression. Dou U by U is equal to dou T by T. You have to take it as a 4, where you have to take the 4. So, your 4 is so you are going to write it as a 4 you have to take here, integrate on both sides, you are going to get it, how much you are going to get, log U is equal to 4 into log T, you are going to get it, that is the log T plus some integral constant you have to use. So, now you simplify this, so what you are going to get it, U is equal to some constant into T to the power of 4 you are going to get it. U is equal to some constant into T to the power of 4, where A is the integral constant you have to use here. So, now not only that, so you able to take, but the energy of radiation emitted per second by unit area of a black body, per unit area of the black body is given by, how we have to write it is that energy of the radiation E is equal to, we know that 1 by 4 into U into C we have to take. So, therefore, you have to substitute this U value here, you have to substitute what is your U value, 1 by 4 a t to the power of 4 into c. So therefore, so which is equal to 1 by 4 a into c, you able to take into t to the power of 4. This a 1 by 4 a into c is the constant. So therefore, is directly proportional to t to the power of 4, you have to write. This law it is. This is the Stephen's law. We are going to take it as a, this law we are going to call it as a Stephen's Boltzmann law. So therefore, what we have to take here, sigma, that is the constant. So that constant is equal to 1 by a into c. You going to take this is very important one. You are going to write it is this constant we are going to call it as a Stephen's constant. Stephen's constant. Clear? From the Maxwell's relations, we able to derive the Stephen's Boltzmann law. Clear? It is very important. Not only that, so we are going to derive the TDS equations by using the Maxwell's relations. How many TDS relations are there? 3 TDS relations are there. So those 3 TDS relations here we are going to discuss. First one, you have to see the entropy S of a pure substance can be taken as a function of temperature and volume. How we have to write it is, the entropy is taken as a function of whom? As a function of temperature and volume, you have to take. Entropy as a function of temperature and volume. So for a differential explicitly you have to take it is ds is equal to dou s is divided by dou t. Dou s is divided by dou t at a constant volume into dt. So at a constant volume into dt plus dou s by partial derivative I have to write it is dou s by dou v at a constant temperature into dV. We are going to write it is dou s by dou v at a constant temperature into dV. Now what you have to write it is multiplying, you are going to take multiply with t on both sides, with t on both sides you have to multiply. So what is going to happen, you have to take, so t into ds, t into ds is equal to t into dou s by dou t at a constant volume into dt plus t into dou s by dou v at a constant temperature into dV. You have to write it is. But you know that, so you know the two things you able to take, Cv is equal to specific heat at constant volume is equal to T into ds is divided by dou t at a constant volume. You have to take, this is the Cv value. Cv is equal to Tds is divided by, so dou t at constant volume. You know that second Maxwell's relation, what is the second Maxwell's thermodynamic relation? The second Maxwell's thermodynamic relation is, what is your second Maxwell's thermodynamic relation? Your second Maxwell's thermodynamic relation is dou s by dou v. Dou s by dou v at a constant temperature is equal to dou p by dou t at a constant volume. Dou p by dou t at a constant volume. So based on that you have to apply here. So therefore Tds is equal to, which one we have to write it is, Tds is equal to, so Tds into dou t by dou t at a constant volume, this entire thing you are going to take it as a Cv into dt plus you able to take the temperature T into dou s by dou v at a constant temperature is equal to, what we have to write it is dou p by dou t at a constant volume into dV. You have to take this expression, we call it as a TDS first equation. What is the TDS first equation? You are going to take it as a, the first TDS equation is the first TDS equation. the first TdS equation is the function of whom and whom you have to take is the function of temperature and volume. So that is equal to TdS is equal to Cv into dt, TdS is equal to Cv into dt plus T into, we have to write it as a temperature and pressure, you are going to take it as a dou P by dou T at a constant volume, dou P by dou T at a constant volume into dV. This is the first TdS equation by using the Maxwell's relations we are deriving. TdS is equal to Cv dt plus T into dou P by dou T at a constant volume into dV. Clear? So like this you have to derive. So not only that, the second TdS equation we are going to take, the entropy of a pure substance can be taken as a temperature and pressure you have to take. The entropy of a pure substance, you are going to take it as entropy. S is equal to as a function of temperature and pressure you are going to take. Entropy is a pure function of, so temperature and pressure you have to take. So you have to do the partial differentiate you able to take. So what will happen? Dou S is divided by dou T. Dou S is divided by dou T at a constant pressure into dt plus dou S is divided by dou P at a constant temperature into, so dP you have to write. This is the expression you are going to take. The similar procedure, multiplying above expression, you have to multiply on both sides, multiply with T on both sides, multiply with T on both sides, you have to multiply. So what is going to happen, you have to say, so you are going to take it as a TdS, TdS is equal to T into dou S by dou T at a constant pressure into dt plus T into, so dou S by dou P at a constant temperature into dP you have to write it. Is clear? So from this what we have to write it is, as it is expression I am writing here, TdS is equal to T into, we are going to take it as a dou S by dou T at a constant pressure, dou S is divided by dou T at a constant pressure into dt plus T into dou S is divided by dou P, dou S is divided by dou P at a constant temperature into dP you have to take. So but you know that, so what you know, Cp is equal to TdS into dou TdS is divided by dou T at a constant pressure you have to take. This is the specific heat at constant pressure by using the fourth Maxwell equation. What is the fourth Maxwell's thermodynamic relations? Fourth Maxwell's thermodynamic relation. Fourth Maxwell's thermodynamic relation. What is your fourth Maxwell's thermodynamic relation? The fourth Maxwell's thermodynamic relation, dou S by dou P, dou S by dou P at a constant temperature is equal to minus dou V by dou T, minus dou V by dou T at a constant pressure you are going to take. Dou S by dou P at a constant temperature is equal to minus dou V by dou T at a constant pressure. That is the thermodynamic fourth Maxwell equation. So based on that you have to write it is, so what is the TdS? TdS is equal to, so T into ds by dt at constant pressure is equal to Cp into dt. This entire term you are going to write it as a Cp plus T into, we are going to take it as a dou S by dou P at a constant temperature is equal to minus dou V by dou T at a constant pressure into dP you are going to write it. So therefore you have to take your second TdS equation in terms of what? In terms of the temperature and pressure is equal to Cp dt minus T into dou V by dou T dou V by dou T at a constant pressure, dou V by dou T at a constant pressure into dP. So this is the second TdS equation we are going to write. Which TdS equation? This equation we are going to take it as a second TdS equation, that is the second TdS equation. Second TdS equation we are going to write. So TdS is equal to Cp dt minus T into dou V by dou T at a constant pressure into so dP, that is the second TdS equation. Now we are going to take the third TdS equation. How we have to write it is, the entropy of a pure substance can be taken as a function of volume and pressure. How we have to take the entropy as a function of S is equal to as a function of volume and pressure you have to take. So you able to take the partial derivative, ds is equal to dou S is divided by dou P, dou S is divided by dou P at a constant volume into dP plus dou S is divided by dou V at a constant pressure into dV. You are going to write it is, it is constant pressure into dV. What we are going to take? Multiply above expression, multiply with what? So multiply with T on both sides, multiply with T on both sides, you have to write it is multiply with T on both sides. So therefore T into ds is equal to T into dou S by dou P at a constant volume into dP plus T into dou S by dou V at a constant pressure into dV. You are going to take at constant pressure into dV. So this one we have to rearrange. How we able to rearrange? Once you have to see, TdS is equal to T into, we are rearranging the term. How we have to rearrange the term? Once you have to see, dou S by dou, first term I am writing dou S by dou P at a constant volume, dou S by dou P at a constant volume into dP plus T into dou S by dou V, dou S by dou V at a constant, which one we have to write it is pressure into dV we are going to take, at constant pressure into dV you are going to write it is. So therefore I have to rearrange this expression. How we have to rearrange this expression? Once you have to see, T into, so we are able to take it as a, how we have to write. So this expression you have to write it is dou S by dou T, first dou S by dou T, I am multiplying with dou S by dou T at a constant volume you have to take. Here also dou T is divided by dou P at a constant volume, you are going to take it at a dP. Suppose you have to write it is I am multiplying with dt and I am dividing with dt, so then get cancelled, therefore the same expression you are going to get it. Similarly you have to do this term also. So dou S by, what we have to write it is dou S by dou T at a constant pressure, dou S by dou T at constant pressure into dou T is divided by dou V at a constant pressure, so into dV you have to write it. But you know that, so according to your thermodynamical Maxwell relations you have to use here. So what is going to happen? You have to see, TdS is equal to, we are going to write it as how we have to take it as a TdS. We are going to write one more term, I have to write it is T into dou S is divided by dou T at a constant volume into, so dou T by dou P at a constant volume into dP plus you are going to take here, so T into dou S is divided by dou T at a constant pressure into, so we have to take it as a dou T by dou V at a constant pressure into, so dV we are going to write it. Clear? So you able to take this entire term, you know that. So what is that? Therefore TdS is equal to, this one you have to take it as a CV into dou T by dou P at a constant volume into dP plus this entire term you are going to take it as a Cp into
what we have to write it is dou T by dou V at a constant pressure into dV. You are going to take this expression, we call it as the third TDS equation. This equation as a function of pressure and volume. This is the third TDS equation. Which equation it is? Third TDS equation. Like this you have to do in your competitive examination. Clear? These are all formulas. So once I will take the formulas, you are getting the confusion. So that's why I am deriving all these things. You try to practice it, then only you able to remember all these things. How you may get questions in your competitive examination? In CSIR December 2017, there was a question, the relation between the internal energy, entropy, temperature, pressure, volume, chemical potential and a number of particles of the thermodynamical system. They are giving du is equal to TDS minus PdV plus mu dN they are giving. This is the internal energy equation, including the chemical potential they are including. So that's why this equation can come. So yesterday I discussed this one. So this is the first thermodynamical function, internal energy. What we need to calculate, if u is a exact differential, then you are going to get it as a thermodynamical relation you are going to get. How you have to going to get, if it is exact relation, how you are going to get it? So dou u by dou s at a constant volume and number of particles is equal to, you are going to get it as a T. Similarly, dou u by dou v at a constant entropy and number of particles is equal to, what you are going to get it? P. So if dou u, your u is equal to, is an exact differential, your u is a exact differential. So what will happen? That is the perfect differential. Your u is the exact differential, you are going to take it as, so what we have to write it is, you are going to take dou by dou v of at a constant dou u by dou s at a constant volume and n, at a constant volume and n is equal to, which one we have to write it is, dou by dou s of, we are going to take it as a dou u by dou v at a constant s and n we have to write it is. So therefore you know that dou u by dou s at constant Vn is equal to T, we are going to write it is. So therefore what we have to write it is, we are going to take it as a dou T is divided by dou V. So n obviously is a constant, instead of V you have to take it as a S, you are going to take, inside part it will come, minus dou u by dou v at constant Sn is equal to minus dou p by dou s, which is the constant, n already is a constant, but inside one you have to take, these are the constant, this is the Maxwell expression you are going to get. What is that Maxwell equation? Dou T by dou V at a constant S comma n is equal to minus dou S by dou P at a constant V comma n. We are going to get, this answer is your answer. Like this you have to do in your competitive examination. This question came for how many marks? So 3.5 marks this question came. We know the idea. So that's why I am teaching all, why I am deriving. While I am deriving, so we have to solve, we will get the solving techniques we will get. If you have to practice 2-3 times, so then whatever I am teaching, those things you have to practice 2-3 times, then only you will get the solving techniques. Otherwise exact question won't get. So the paper will twist and paper will tilt and paper will question you, paper will you drag you, so paper will select you over the great aspirant. So that's why, so people whoever do the great hard work in that subject, those people only will get the benefit. Thank you so much. So today we are teaching the Maxwell equations and applications of the
some of the applications of the Maxwell equations I told you. Maybe in the next class some more applications of the Maxwell equations I will teach to you. Thank you so much.